Right, so what we can do, so here no coordinate system is established for us, so we can make our own. So the most common is going to be x to the right, y up. But there are instances where you might not want to use that. Right, so what we can do is we can put both vectors, and just for convenience, I'm going to put them at the origin here. So this is my 101 millimeter vector. I'll call that F1. And then I have the 183 millimeter vector, which I'll call F2. And that is at 55 degrees from the horizontal. So I'll be more formal once we get to chapter 3 in kind of the solution steps we want to go through, but I will put in the find. So what I want to find, I'm going to call the resultant vector R with the overbar. I want as a vector, what is R? Which is going to be, just for the note, F1 plus F2. Right, so that's where we want to end up. So the question is, how do we add together F1 and F2? So first, we don't know what is F1 bar, what is F2 bar. We just know their magnitudes at the moment. That's all I have written. Once we know those, then we want to add them and then find R. And we want this to be in polar form at the end also. Right, so where do we start? We've established a coordinate system. I said x is right, y is up. X is also the I hat direction. Y is also the j hat direction. Right, so let's start with an easy step, and then we can work to the slightly more complicated step. We want to express both of our vectors in component form. So let's start with the easier one, F1. So we need to find F1 as a vector. So we need to find how much of F1 is in the I direction, how much of it is in the j direction, which is to say how much is in the x direction, how much is in the y direction. So let's start with the first part. How much of F1 lies along the x direction? Right. In this case, F1 points to the right. It's parallel to the x-axis. So all of it lies in the x direction. So all 101 millimeters of it lies in the x direction. So I hat is a vector. So this says 101, its length is 101 in the x direction. And then how much of it is in the y direction? Right, so just 0. So for just completeness today, I'm going to put the whole, I will explicitly put 0j here. All right, so vectors have components to it. So I have I and j. It also has units. It has millimeters with it. So this is a full statement of expressing F1. So again, if I'm calling it a vector, I have to have either components or I have to express it in polar notation, which we'll do at the end. And I need units with it. All right, so F1 was easy because it was just in the, it pointed to the right and we didn't have a lot of problems there. So now the trickier one is how do we express F2 as a vector? So it's going to be the same idea. We want to know how much of it lies in the I direction or along the x and how much lies along the y direction. So here it doesn't point only to the right or left. It doesn't point only to the up or down. So how do we find how much of it is just in the horizontal or the x direction? Right, so I'll, for today, kind of explicitly draw this, but in the future I won't. So again, we can break this down into two equivalent. So I'm just talking about F2 for right now. Instead of going from here to here, I can go to the right, and then I can go up, and that's the same, I get to the same place. But basically, so I know now, I don't know how far I had to go this way, but I know I went only to the right. And I don't know how far I went this way, but I know that I only went up. So I need to find what these lengths are, and then I know that this is now only in the x direction. This is only in the y direction, which corresponds to I and j. We didn't have to do that in the first one because it was already only going to the right. So what we know is we have this right triangle here. We know the hypotenuse is 183 millimeters, and we know this angle here is 55 degrees, and we know that those are orthogonal, so it's just a right triangle problem. So how much of it, you don't need it as a decimal number right now, but how much of it is in the I direction then? Right, so we're talking about, right, so this one's the magnitude times, right, the component, in this case, the adjacent. So cosine 55, and that much is in the I direction. All right, so that's how much is horizontal, or in the I. And then how much is in the Y direction? It's going to be the opposite leg. Right, so that's sine 55J. So this does have both I and J components. Now I can express this as a decimal because it'll be easier to work with then. So that's going to be 105I, and that needs millimeters. Right, so I've expressed this now in IJ components. So that was step 2 in the methods slide. So now I'm ready, now that I know F1 bar and F2 bar, I can now find the resultant. So I know that R is going to be F1 plus F2. So now that they are in component form, F1 and F2, I can add the like components together. So that's going to be 101I plus 105I plus the J component, so 0J plus 150J. So that's the resultant vector, and we can sketch this, which will help in the next step. So roughly, it'll look like that, kind of. So this is correct. This is the vector. This is the resultant vector in component form. But the question is asking, find the resultant position vector in polar form. So for this particular one, we're not quite done. Even though it's not wrong, it's just not expressed the way that they want it. We want to be able to give someone a length to walk and a heading to take. So we want a polar form rather than the Cartesian form. So now what we're going to do is kind of go in the opposite direction. We know R, if we go to the right by 206, and then we go up by 150, that we're going to get to R. So now we want to go, we know the legs, and now what we want to find is the magnitude, which is the hypotenuse, and we want to find its direction. And direction, assume, is going to always be measured from the positive x-axis, which will be more important in the next problem. So how do I now take this information and express it in polar form or magnitude direction form? Right, so if I want to find the angle, I can use arctangent is my easiest one. So because I made this little sketch here, it's going to be easier to look at. So it's going to be opposite over adjacent. So you should get to 3 digits, 36.1 degrees. And not only is it measured from the positive x-axis, but by convention, it's counterclockwise from x. So positive 36.1 degrees. And then how do I find the magnitude of R, which I can express 2 different ways. So R as a scalar value, we're assuming it means the magnitude. Yeah.
Is the denominator be 206?
Yeah, sorry, 206. So the magnitude of R, which I can express either as R without anything over it, or R bar in these absolute value signs, they mean the same thing. This is going to be a scalar quantity. how do I find the magnitude of r?
Square root of
Right. So it's just the hypotenuse, so it's the Pythagorean theorem, or the distance formula, same thing. So it's the square root of the sum of the squares of the components. In this case, I have two components, but once we get to 3D, it's actually going to be the same idea. So I take the square root of the sum of the components, and I get 255 millimeters. Two things to note here, or one thing to note, I guess. The magnitude carries the unit of the vector. All right, so now I can express r as a vector. Kind of the alternative way, or the polar way, will be 255 angle 36.1 degrees millimeters. So these are equivalent in that this has a magnitude of 255, this has a heading or a direction of 36.1. I haven't changed r bar, I've just expressed it in a different way.